Okay, so I would like to cover today this topic of equivalence relations. I wasn't sure it's the right time to introduce it because it is a bit tricky to understand. I mean, not necessarily because it's hard, but because it's a bit different than what you are used to, and it takes some time to digest. But I think we can try to do it today and come back to it later on if needed. And the basic motivation is we defined, I guess, the basic motivation that I can explain at this point comes from a foundational question. That is, we defined the natural numbers as sets, and we would like to define the integers and the rational numbers also as sets. So let me just postpone the definition of integers and even of negative rational numbers, but let's suppose we only want to define positive rational numbers. And so this I will denote as q bigger or equal than 0. And intuitively, I would like to say that this is all the quotients A over B, such that A and B are natural numbers, and B is non-zero. However, we have a problem because if I do it from a foundational point of view, then 1 over 2 is a different element than 2 over 4, which is right. It's like, I mean, if I'm like just using this A over B as an official symbol, then before doing anything, A over B, I mean 1 over half, 1 over 2 is different than 2 over 4, which is different than 4 over 8, and so on. So I would like to have an operation that identifies let's say formal quotients that I want to consider to be the same. So this you can think intuitively as kind of a gluing procedure. We have some set and we want to to kind of pinch some subsets in it into actually one element. But what does it mean to be equivalent? So intuitively, so we need a notion of equivalence. Let me denote it as tilde. So we would want to say, for example, that 1 over 2 is equivalent to 2 over 4. But what are the basic properties that we expect from an equivalence notion? This is given in the following definition. Okay, or maybe I'll postpone the definition. What we want as properties, basically, we want it, I mean, for notion of equivalence on a set X, we want first that for any X in X, X is going to be equivalent to X, right? Otherwise, it wouldn't make any sense. Second, we want that for any X and Y in X, if X is equivalent to Y, then Y is equivalent to X. This is called symmetry, by the way. And the first property is called reflexivity. And the third property is that for any X, Y, and Z in X, if X is equivalent to Y and Y is equivalent to Z, then necessarily X is equivalent to Z. Right? We would like to be able to move around with this equivalence. So if I know that X is equivalent to Y and Y is equivalent to Z. In this, you can imagine is like I have some kind of path from X to Y. This is the equivalence between X and Y. And I have some path between Y and Z. Then I can concatenate the path from X to Y and Y to Z and get a new path from X to Z. So this property, this is called the transitivity. This is I mean, the whole three properties, I guess you could say, are what intuitively we want from an identification relation on a set. And so to be more formal, slightly more formal, let X be a set. A relation on X is a subset, let's call it R, of the Cartesian product of X with itself. Okay, so R is a set of pairs A, B, and if A comma B is a pair that is indeed an element of the relation R, we denote ARB. Okay? And a relation R on X is an equivalence relation if it has the three properties. So I'll just rewrite it for any A in X. We have a relation between A and itself. This is the same again in our notation. It's the same as saying that the pair A comma A belongs to R. Two, for any A and B in X, A comma B belongs to R if and only if B comma A belongs to R. So this is, again, it's the same as saying that we have ARB if and only if we have BRA. And third, this is the transitivity if, or for any elements A, B, and C in X, if A is in relation to B and B is in relation to C, then A is in relation to C. And when a relation is an equivalence relation, we denote A tilde B whenever A is in relation to B, which is again is the same as saying A comma B belongs to the relation.
I have a question as the need for I, like the first the symmetry, was if you already have if you have the symmetry and the transitivity, do you need no sorry the do you need the reflexivity?
Yeah,
right?
you cannot deduce formally reflexivity from symmetry and transitivity. If you think of it, I mean, because to get reflexivity, you need to know that A is in relation to A.
Yeah.
How would you do that? I mean, suppose A is in relation to B.
Yeah.
Then by symmetry, you know that B is in relation to A.
Exactly.
But how do you I mean, how do you construct? I mean, how do you deduce that A is in relation to A?
Well, because of the transitivity, A is in relation to B,
Yeah.
which also means that B is in relation to A. So by
Yes.
transitivity, A is in relation to A.
No. So transitivity,
Yeah.
you should think of it as a triangle, right?
Yeah.
I have A, B, and C. A is in relation to B.
Yeah.
Then you get, but what is your C?
A. So the triangle is a segment because a segment is a singular triangle.
Oh, I see what you mean. A is in relation to B. B is in relation to A. And then you're right that A should be in relation to but we don't, okay, this is true. If you know that A, B, that there exists some pair A comma B for which A is in relation to B, then you can indeed deduce that A is in relation to A. But you a priori, you don't know that there is even one pair. You take an element A, and you don't know that there exists even one element B for which A comma B is nil. So you really need, this is kind of an anchor.
Right. Yeah, because indeed, like if your equivalence is only about 1 point, yeah, then you don't have.
Yes.
Yep. Yep. Okay.
Yeah, it's a good remark. Any other questions on the definition? Okay, so as examples, the first example is I claim that if f is a function from x to x, then it defines a relation on x. I mean, I will say that A is in relation to B if and only if, this is like, it's like a definition, right? If and only if f of A is equal to B. Right? So in other words, I mean, we actually have defined a function as a subset of the Cartesian product of x with itself. So in this definition, I mean, you can view, I mean, if we view f as simply a subset of x times x, then it is a relation. I mean, a relation is simply any subset of pairs of x with itself. However, it is not necessarily an equivalence relation. Can you think of what can go wrong? What can be a problem for a function to define an equivalence relation?
I guess bijectivity has to be, because you need to be able to have reflexivity.
Yeah, but even if you have a bijectivity of the function, you don't necessarily get an equivalence relation.
Oh.
Right? Because let's say
Oh yeah.
I mean, just take this is, it's always good to do like examples with the finite sets. I have A, B, and C. I can define a bijective map that shuffles A, B, and C. So let's say A goes to B, B goes to C, and C goes to A. Right? And then even if it's bijective, I mean, you see that I don't have for example, I don't have reflexivity. So unless you have, I mean, unless you have the identity function, then you don't have an equivalence relation.
It doesn't talk about the function has to be from the same, like from the same set to onto itself.
Yes, of course, that's kind of a prerequisite.
Yeah.
Otherwise, you don't have a notion. I mean, one can give a more general notion of relation between the two sets, x and y, but we don't do it now. So this is almost never an equivalence relation. However, there is one main example of equivalence relation that we will consider. So, so take X to be the set of integers. And we set A equivalent to B if and only if A is equal to B modulo N. This means that when I write A as, when I do long division of A by N, I mean, I get, let's say, Q1 N plus R1, and I do long division of B with N, I get some Q2 N with R2, then R1 is equal to R2. Right? The remainder of long division of A by N and long division of B by N is the same. And I claim that this is an equivalence relation. So let's see it. Then I claim that tilde is an equivalence relation. So first, we need reflexivity. So reflexivity is immediate. It means, I mean, of course, A is always equal to A modulo N. Symmetry is also immediate, right? I mean, if A is equal to B modulo N, then immediately B is equal to A modulo N. And transitivity is also easy. I mean, if A is equal to B modulo N, and B is equal to C modulo N, then, I mean, the remainder of A by long division with N is the same as the remainder of B with long division by N, which is the same as the remainder of C with long division. So, so A is equal to A to C modulo N. Okay, so now that we have this notion of equivalence relation, we would like to do the gluing procedure. And for this, we do a construction as follows. So let X, or let tilde, be an equivalence relation on X. For an element X in X, denote bracket X as the set of all elements Y in X, such that X is equivalent to Y. This is called the equivalence class of X. And let's inspect this this notion and note that if so of course the equivalence class of an element is simply a subset of X, right? And if I have two elements, A, B, in the equivalence class of X, then A is equivalent to X by definition, or actually, I wrote it in the other direction. So X is equivalent to A, and X is equivalent to B. But by symmetry, I get that A is equivalent to X, and by transitivity, I would get that A is equivalent to B. So here I have by symmetry A is equivalent to X, and I also know that X is equivalent to B. Hence, A is equivalent to B by transitivity. Okay, so the equivalence class of X, I mean, all the elements in the equivalence class of X are equivalent to each other. And there is another property of this equivalent class of X, and that is what happens if I look at different equivalence classes. So let X and Y be two elements in X, and consider the equivalence class of X and the equivalence class of Y. If so, these are two subsets of X, right? So if their intersection is non-empty, then there exists some element Z in X such that Z belongs to the equivalence class of X and Z belongs to the equivalence class of Y. And this is to say that Z is equivalent to X and Z is equivalent to Y. But then I get, as before, by symmetry and transitivity, that X is equivalent to Y. Right? I mean, if Z is equivalent to X, then X is equivalent to Z. This is symmetry, and by transitivity, X would be equivalent to Y. But if X is equivalent to Y, I claim that the equivalence class of X is the same as as sets, is simply the same as the equivalence class of Y. So this implies that the equivalence class of X is simply equal to the equivalence class of Y. So if I found one element that is common to two equivalence classes, then they completely identical. And of course, the complement of this property is that if X and Y are not equivalent, then their equivalence class is completely disjoint. You cannot find even one element in common. So otherwise, or maybe let's say it like this. Thus, if the equivalence class of X is different than the equivalence class of Y, then necessarily the equivalence class of X intersection with the equivalence class of Y is the empty set. So you can think of it this way. Let's do like a simple diagram. This is X. And I have some equivalence relation on X. And this equivalence relation divides X into disjoint subsets. So this would be maybe the equivalence class of X1. This would be the equivalence class of X2. This would be the equivalence class of X3, for example. So this, if you want to get like exactly this drawing in a concrete example, take the integers and the equivalence relation is modulo 3. So two integers are equivalent if they are equal modulo 3. And then what are the possible equivalence classes? All possible equivalence classes are, first, I have the equivalence class of 0. The equivalence class of 0 is, well, 0, of course, belongs to the equivalence class of 0. And then any integer that is equal to 0 modulo 3. So I have 3 minus 3, 6 minus 6, and so on. By the way, of course, since 3 is equivalent to 0 in this relation, then the equivalence class of 0 is the same as the equivalence class of 3. The second equivalence class is the equivalence class of 1. This I have 1, I have 4, I have minus 2, and so on. Sorry, did I want minus 2? Yeah, I subtract 3. Yeah. Okay. And of course, this is equivalent to the, for example, the equivalence class of 4. This, of course, you have infinitely many ways to write the same equivalence class. And the third equivalence class is the one of 2. I have 2, 5, minus 1, and so on. Okay, so if I look at this this is kind of a canonical way to write equivalence classes. And I get that the collection of all equivalence classes is what is called the partition of the set X. Note for any equivalence relation, tilde on X, the collection of all equivalence classes I will call it Q. This is the collection of all equivalence classes X, such that X is some element in the main set, the ambient set X. This you should note that when I write this definition, I mean I take the set of all equivalence classes of X of the relation. This set has a lot of repetitions, right? I mean, whenever two elements are equivalent, their equivalence class will be the same. But nevertheless, I can write set because in set we remove repetitions. And the collection of all equivalence classes of the relation tilde is satisfied or is what is called a partition. And a partition simply means that first, any two elements in Q, I mean, elements in Q are simply to some equivalence classes, are either equal or disjoint. And second, if I take the union of all elements in Q, when I take the union of all equivalence classes that appear in Q, then I get back my original ambient set X. Okay, and the picture again is like equivalence classes or equivalence relations always give you some partition of the original set into disjoint part that cover the entire set X. Any questions so far? Okay, so I will simply be slightly formal with this equivalence classes, and I will say the set of all equivalence classes is called the quotient of x by tilde. And noted x, so x divided by tilde, or x modulo tilde. This is our notation for the set Q. So in other words, when I mean, the way to glue elements in a set according to some equivalence relation is simply taking the collection of all equivalence classes. Right? So, and again, intuitively think of the integers and the equivalence relation modulo 3. We want to glue integers according to this equivalence relation. So we simply take the collection of all equivalence classes with respect to this relation. And what we get is actually it's a set of 3 elements, right? Let's just scroll back to this modulo 3 example. If I take, I mean, the quotient integers modulo the equivalence relation given by modulo 3 is simply the set of all equivalence classes. But the set of all equivalence classes, I can write it as the set of equivalence class of 0, equivalence class of 1, and equivalence class of 2. Right? It's a set with 3 elements, 3 distinct elements. Of course, I could also write it as the set of equivalence class of say 4, set of equivalence class of 2, and the set of the equivalence class of what do I have here? So this is 1. I need something for 3, so let's make it minus 3. Right? This is an equivalent way. This is the same way. I mean, just a different way to write the same set. Okay, but in any case, this is a set of 3 elements. So this is the reason that the intuition is that I glue. I take a lot of I mean, a lot of numbers that are the same in modulo 3, and I think of them as one element. So that's the reason behind the term quotient. Now, I claim actually that the process I did with starting with an equivalence relation and considering then the equivalence classes, which are a partition of the set X, and then considering the quotient as simply all the elements in the partition, this process can be reversed. Namely, if you give me, let me write it down. So conversely, suppose X is a set together with a partition. Let's call this partition P. P what is a partition? It's a collection of subsets of X. So it's a set of UI. I is some element in an index set I, where each UI, so for each index I in big I, UI is a subset of X, and such that, I mean, this is the two properties of a partition. First, if I take the union of all UI for I in the index set big I get the set X. And two, if well, for any I and j, I and j in big I, either UI is equal to uj, or UI is disjoint with uj. Okay, this is the defining property of a partition. And if I have such a structure on X, I can define an equivalence relation. Define a relation tilde on X by setting A equivalent to B if and only if there exists some index I such that A and B belong to the same UI. And this is easily seen to be an equivalence relation. Tilde is an equivalence relation. Let's check it. I need reflexivity. Reflexivity, I take, so let A be some element in X. Since the union of all UI is X, there exists some index I in big I such that A belongs to UI. Right? What does it mean to take the union of a collection of sets? It means I look at all elements that belong to at least one of the sets in the union. So if the union is X, then it means that for any element in the ambient set X, there exists some UI for which it came from. Sorry?
How is this reflexivity?
So once I know that A belongs to UI, then I know that by the definition of the relation that A comma A, I mean A equivalent to A. because the relation said A and B are equivalent if they belong to the same set, to some set UI. So A and A is, I mean, we take the pair A comma A. Both of them are, I mean, assuming, I mean, we have that A is an element of UI. So obviously, the other A is also an element of UI, and by definition, it means that A is equivalent to A. Kind of, it's trivial once you just unravel the definition. It's not anything sophisticated. To see symmetry is obvious because I mean, clearly, if A is equivalent to B, then there is some UI such that both A and B are in UI. But then obviously, I mean, B is equivalent to A. And, I mean, the relation we defined is immediately symmetric. And transitivity is also the same. It's also very easy. Transitivity if A is equivalent to B, then AB are elements in UI. And if B is equivalent to C, then BC are elements in some UJ. But then B is an element in UI and an element in UJ. So I has to be equal to J. So let's say UI is equal to UJ. And if UI is equal to UJ, it means that A, B, and C are simply in the same set. Let's say UI, and this means that in particular that A is equivalent to C. So the picture is that I give you a set. Any partition of the set gives you an equivalence relation, and as a result, you can take the quotient. The quotient is simply just the different equivalence classes or the different sets in the partition. And if I give you an equivalence relation, you get a partition. It's an equivalent way of describing the data, right? So every equivalence relation gives rise to a partition. Every partition gives rise to an equivalence relation. And once I have one of these types of data, I can take the quotient, which is simply either the set of all equivalence classes or simply the collection of all the sets in the partition. It's time for a break, but before we do that, do you have any questions?
I do have a notation question, so if
Yeah.
people have questions connected to the contents. Okay, the notation I have, the question I have, if you could scroll back back to when you define the quotient, yeah, right here.
Yeah.
You define x divided by tilde equals, like you have colon equal q.
Yeah.
And in other places you've used equals def.
Yeah, it's the same.
It's the same.
It's
Okay.
the same. I mean, I tend to like this colon equal a bit more because it gives you a direction. I mean, it means this is a notation that is not defined. I mean, we now define a new notation and we use something that we previously defined. Okay. But you can, yeah, you can write either. Other questions? So let's meet in 10 minutes. Okay. Let's get back. We talked about the formal definitions of equivalence class and quotient, and I'd like to illustrate it with a few examples. We start with very easy examples. I mean, I take X to be the set of the numbers 1 up to 7. And let's draw it like this: 1, 2, 3, 4, 5, 6, and 7. Then I can illustrate an equivalence relation by this diagram. And what I get is that the quotient of X by this equivalence relation is the equivalence class of 1, the equivalence class of 2, and the equivalence class of 5. Right? Here, I simply mean whenever two circles are connected by a line, then I consider them equivalent. And of course, this quotient set can be written in other ways. For example, I could do the equivalence class of 4, the equivalence class of 3, the equivalence class of 7, and that's the same thing. Now, going back to this foundational question of how to define the integers and the rational numbers given the definition of the natural numbers. So this is the main example. I take X to be the Cartesian product of natural numbers with itself. Define a relation tilde on X by setting a pair A comma B is considered equivalent to a pair A prime comma B prime if and only if A plus B prime is equal to A prime plus B. What I'm doing here is I think of the pair A comma B as representing, or I mean, I wanted to represent the quantity A minus B. So I should say maybe if we want to be more formal on the foundational level, I mean, on N defined as sets, we have the operation plus. I mean, to do addition of numbers when the numbers are defined as sets, like the 0 is the empty set, 1 is the set containing the unique element being the empty set. Remember that the number n is simply defined to be all the numbers up to n minus 1. Right? This was the definition we had of n is exactly this. I mean, you can see it like 0 is the empty set, 1 is the set containing the empty set, but the set containing the empty set is simply the set containing 0. And 2 is 1 union the set containing 1. But what is that? 1 is the set containing 0. Union 1, this is the set of 0, 1. Right? So you see, it's a bit funny, but I mean, in this definition of natural numbers as sets, the element n is simply the collection of all numbers that previously defined before n. And then, of course, we have an operation of addition. I mean, n plus 1 is defined, right? N plus 1 is simply n union the set containing the unique element n. And by induction, I can define n plus k. N plus k would be n plus 1 plus 1 plus 1 k times. So we do have an operation of addition on the set of natural numbers defined in this way. And now we want to define the integers. So how do we define the integers? I kind of want to represent the quantity a minus b. And if I can represent the quantity a minus b, then of course I take, for example, I take a equals 0 and b equals some integer. I get all the negative numbers. But of course, a minus b can, I mean, if I simply take all pairs a comma b, then I get a lot of redundancy. So I need to define an equivalence relation to identify pairs A comma B that would represent the same quantity A minus B. And to do that, I simply say, okay, I define an equivalence relation by saying that two pairs like this, AB and A prime B prime, are equivalent if A plus B prime is equal to A prime plus B. And this is well defined even from a foundational point of view, because I do have this notion of a plus between natural numbers as defined as sets. So let me just show you that this is an equivalence relation. Tilde is an equivalence relation. Clearly, we have reflexivity. I mean, A comma B is always equivalent to A comma B for any element A comma B in the set X. I guess I remind you the set X is simply n Cartesian product with itself. A symmetry if A comma B is equivalent to C comma D, then by definition, A plus D, again, just keep this in mind. I mean, A comma B represents A minus B, and C comma D represents C minus D. And we want to think them as equal if when I don't have a subtraction of natural numbers as defined on the foundational level as sets, but I do have addition, so I can say that A minus B would be the same as C minus D if A plus D is equal to C plus B. And assuming that I have this relation, then obviously C comma D would be equivalent to A comma B, because I can simply reverse the equation. I mean, C plus B is equal to A plus D. Okay, so I have symmetry and transitivity. If A comma B is equivalent to C comma D, and C comma D is equivalent to E comma F, then I'll just write it in one line. A plus D is equal to C plus B, and C plus C plus F is equal to E plus D. And what I want to show for transitivity that AB is equivalent to EF. But to do that, it's the same as saying that A plus F is equal to E plus B. But from these two equations, I can add them two together. And I get that A plus F plus D plus C is equal to E plus B plus C plus D. And C plus D and C plus D can cancel out. So I get that A plus F is equal to E plus B, as I want. Is it okay, Andre? Okay, so I get an equivalence relation, right? And now define the integers to be this set, n times n, modulo this equivalence relation. And you see that the equivalence class, the equivalence class the equivalence class of a pair A comma B is the set of all pairs C comma D, such that okay, I'll just repeat the definition, but this means that A plus D is equal to a C plus D, C plus B, right? Which is again, it's the same as saying, that A minus B is equal to C minus D. Okay, so I simply, in this way, I have defined a representation of the integers using only what I had previously defined as sets. Now, okay, the next example is the rationals, but do you have any questions about this example?
Yeah, I have a bit of a problem. Okay, I understand that's an equivalence class that contains all the numbers. There are basically all the results of subtraction that end up with interesting numbers. For example, let's say 2 being 3 minus 1 and 7 minus 5. Yeah. But I'm still having a bit of a conceptual leap to do to understand that this is indeed a definition of the subtraction itself.
So this I didn't claim. I claim that I can define the set of integers. I didn't claim that I'm now defining the operation of subtraction.
Okay. So you're defining the set of integers, but had you not done that already when you defined every single set? So every single number via sets?
Well, okay. That's you're in principle right that I could have defined the integers by just declaring a formal symbol for every natural number. I declare a formal symbol of, I don't know, for every natural number A, I declare A bar to be some element, some set that is distinct from A.
Right.
And then I take the set of integers to be all all the natural numbers A and all their distinct sets, new sets A bar. But in this definition, I mean, this definition of the integers that I gave here would be much more easy to work with when you want to define now the operation of addition and subtraction. Let's say addition is very easy, because if you have a pair A comma B, you have a pair. Okay, so let's say, I guess, well, I don't want to get into too many details of these foundations, but this would be, let's say, one option to define the integers. I think in the example of the rationals that we see now, you will be maybe more convinced that this is kind of a canonical way to do it. So let me sketch it. But just to generally answer your question, this definition of the integers is much more easy to work with when you actually want to define the operation of addition and subtraction.
Sorry, I'm going to be annoying.
No, it's fine.
But for this definition of the subtraction, you are using the addition already, because you have A plus D equals plus B.
I'm using addition of natural numbers, not addition of.
Of course. No, yeah, I get it. Gotcha.
Okay, so let X be the set of integers Cartesian product with the set of non-zero integers. So I write it like this: integers minus the set with the single element 0. Define an equivalent, a relation tilde on X by setting a pair A comma B is equivalent to a pair C comma D if and only if A times D is equal to C times B. So here I'm secretly assuming that we have defined multiplication of integers. So this is just to be complete, assuming we have defined a multiplication of integers. A multiplication of integers, again, I don't want to do all the details of these foundational constructions, but you can imagine it's not that hard to define multiplication of integers, because I know how to define, let's say, I can define addition of integers in a very similar way that I defined the addition of natural numbers. And then I can define a multiplication as just addition. Yes, multiple addition. So given a definition of multiplication of integers, I can define an equivalence relation like written here. And now I think of AB, the pair AB, I think of it as A divided by B. And of CD as C divided by D. And I say that they are equal if, again, like in elementary school, I mean, if A times D is equal to C times B. And this is an equivalence relation. So tilde is an equivalence relation. I can do the details, but I think you can do it as an exercise if you want. Well, obviously, the pair A comma B is equivalent to itself. Then for reflexivity, I mean, if the pair A comma B is equivalent to the pair C comma D, then just reversing this equality give you, I mean, then we know that AD is equal to CB, which is the same as saying that CB is equal to AD. But then, by definition, this means that CD is equivalent to AB. Okay, so the relation is clearly symmetric as well. And transitivity, let me just write it intuitively. I mean, if you know that this AB is equal to CD, and you know that CD is equal to EF, then you manipulate the equations and you get that AB is equal to E over F. Right, I leave the details to you as an exercise. It's very similar to what we did before. And I define the rational numbers as the quotient. You take integers, I mean a pair of integers such that the second coordinate is non-zero, and you mod out by this equivalence relation. Okay, so and in a similar way, one can define addition and multiplication on the rational numbers. I mean, we have post priori way to. So
because that's using the density of Q in R.
It's but of course when we define R from Q, we don't know in advance. I mean, we don't have in advance the density of Q and R.
Okay.
Right, but it is so okay. But this is it's a nice reading of how to define kind of axiomatically or from foundational level. Let me just even erase this. You can read the full definition of Dedekind cuts in many places in the internet. I want to do I think 2 more examples. Yeah. So So now I'm getting out of the realm of these foundational issues, and we assume that we have the real numbers. We have the real numbers, and I can consider the set X to be the real dimensional plane. So this is R2, this is R Cartesian product with R, which I mean, as you saw in high school, it's like the set of all pairs XY such that X and Y are real numbers. Define an equivalence relation tilde on X by setting X comma Y equivalent to Z comma W if and only if X squared plus Y squared is equal to Z squared plus W squared. And I leave it for you as an exercise to check that this is indeed an equivalence relation. Now, the equivalence class of a pair X comma Y in R2 is the set of all pairs Z comma W such that so I guess just to maybe stress the what we fix and what we so suppose I take some particular point x x0 y0 and I want to consider I want to identify the equivalence class. Take a particular point x0 y0 and I want to identify the equivalence class of x0 y0. So now I let z and w vary, and I'm looking for all pairs z and w such that z squared plus w squared is equal to x0 squared plus y0 squared. So let me denote x0 squared plus y0 squared. I denote it as r, or maybe r0. This is a positive number, so in fact I could even denote it. I mean, it would be some square of a non-zero number, and the set of all zw such that z squared plus w squared is equal to r0 squared are simply the elements on the circle with radius r0. It's all Z W whose distance from the origin is R0. And in fact, somewhere on this circle lies also x0, 1, 0, y0. Because the x0, y0 also satisfy that x0 square plus y0 square is equal to r0 square. So you see, the equivalence class of an element is all the elements that sit on a circle centered around the origin, passing through this through this element. And we have many different equivalence classes, right? We have this white circle is representing one equivalence class, the purple representing another, and the blue will represent even another equivalence class. So now I want to consider the quotient. What is the quotient? I mean, of course, we can say on a formal level, the quotient is just the set of all circles in the origin that are centered around the origin. And every circle is a different equivalence class. But instead of a set of circles, I mean, this is just a set of points, and I can pick in any circle a representative. I mean, I can choose a line passing through the origin. Let's say this line. And I choose one element in every circle that intersects this line. So in this way, I can identify I can identify the set of equivalence classes of this example with simply one given line that passes through the origin. Okay, and this you can, let's say, you can see intuitively that this kind of preserves the geometry, because if I take the set of equivalence class of circles, I have a notion of distance between two equivalence classes. That is the difference between the radius. And instead of looking at it like this, I can also look at the line. And on the line, I choose the points, and the distance between any 2 points would be the same as the distance between their representing circles. So in this way, I do preserve. I mean, the quotient set by the equivalence relation kind of inherits a geometry, or at least inherits a notion of distance, and I can represent this set of equivalence relations with distance in several different ways. In fact, of course, I didn't have to choose this line. I could have chosen another line like this. And I take all the points here. Any questions on this?
What we maybe missed the beginning of this session. This was, what does it define of what's?
So I take the set of all. I mean the set of tuple. I mean ordered pairs of real numbers, the plane, and I define an equivalence relation like the one in blue.
Okay, it's clear. It's not clear where it is going.
No, this is just to give you an example in which the set of equivalence relations inherits the additional structure that came from the original set on which the relation was defined, right? On the set of pairs of real numbers, I have a notion of a distance. This is the Euclidean distance. And then if I do a nice equivalence relation, this is not always true, but for a nice equivalence relation, I get some induced notion of distance.
Could we use this to, like we're effectively creating a partition of the plane, right?
Yeah, it is a partition.
Which is parameterized by the distance of any point on the circle to the center. Could we actually use this as a definition of the real numbers? Because we take any circle centered into the.
It will be circular because because in order to even define the set X, you need numbers.
Right. True. Yeah.
So. Okay, let me just give you a sketch of something that we will see later on. But this is called the projective line. I stress that this is just a sketch because I don't want to get into the whole details, but I think you can already understand some. I mean, the direction of where we're going to use equivalence relation in this construction. I mean, so I take the set X to be the set of all points in the plane that are not the origin. So this is like the punctured plane. And define an equivalence relation on X by setting X comma Y is said to be equivalent to X prime comma Y prime if and only if there exists some non-zero scalar such that xy is equal, sorry, well, such that x prime y prime is equal to lambda x lambda y. In other words, I simply say that x comma y is always equivalent to lambda x lambda y for any non-zero lambda. And it's easy to check that this is an equivalence relation. And so now I take, I define the projective line to be the quotient of this set X, or let me just write it explicitly, the set of all points in the two-dimensional plane. that do not include the origin modulo this equivalence relation.
Why not including the origins? These are lines that definitely.
Because if I include the origin, then any point will be equivalent to any point. If 0, 0 is included in the set, then take any non-zero number lambda, scalar lambda, and you get that. I mean, lambda times. Yeah. So wait. Do I? Yeah. If you take a 0, 0 to be in the set, and you declare the equivalence relation like I did here,
Yeah.
yeah. Well, I guess it would not be true that everything is equivalent to everything, but I will get some point for which is not equivalent to any of the other points, to anything else, in fact. And what are the? I mean, how do I describe the equivalence classes? The equivalence classes, I mean, one particular equivalence class of, let's say, some xy is the set of all points that sit on a line passing through the origin. And passing through the point xy. So an equivalence class in this relation can be described as simply a line passing through the origin. And I have many lines passing through the origin, right? Each of these lines would be a different equivalence class. So the quotient set is the set of all lines passing through the origin. And I can use a slightly different geometric description by saying I take the circle with radius 1. This is called the unit circle. On the circle with radius 1, for every vector, I mean for every element in the circle, I identify the so-called antipodal element. This is the element when you take a minus on both of the coordinates. And the projective line can be equivalently described as the unit circle when I identify two antipodal points.
Okay.
And if you identify two antipodal points, in fact, you get another circle, because you can say, for example, you identify these antipodal points. This is like taking the circle, dividing it into two halves, and gluing them one on top of the other. But of course, this point is identified with the antipodal points here. So I get again the circle. Okay, so this is just to give you a bit of a glance to the future, but we will come back to it later on. Sorry, I went over time, but are there any questions on what we did here? All right, then see you next week.
Wait, I have a question actually. That's not math related. Next week is a holiday. So is there gonna be a class?
Which holiday, by the way?
Class? Himmelfahrt, yeah. Ascension, I think.
Yeah,
it's called.
Ascension.
Okay, they're going up.
Exactly.
Okay. There's going. I differentiate between going up and going down vacations.
Right, yes, so this is a going on vacation. So I'd love the going down vacation, but just saying.
Okay, so yeah, let's take a vacation next week and.